troubleshooting inputs and outputs doesn't have to be any kind of rocket science. It's not as complex as it might seem, providing that we know how things work and why they work the way they do. So now we look at a input right there coming from a terminal. This could be a brick PLC, it could be a PLC card, it could be anything. You're going to have all the screw terminals of the PLCs connected, numbered 0 through whatever. The most common is 16 terminals, but you could have as many as 32. Now, for every screw terminal, right, you're going to have a light emitting diode or an LED indicator that tells you the condition of that screw terminal. Now, the input itself, one side of that input is connected to the power source, typically a common. The other side of that power source is coming into the common terminal on the card or the terminal strip. Now, as long as this input is open, there is no current flow through that circuit. Now, the circuit right there itself is not as complex as it might seem. This block diagram breaks down the parts of that circuit. You have right here the actual input device, in this case the limit switch. That's connected to the power source. Both the limit and power source are connected to the screw terminals. Okay, now behind the screw terminals you're going to have a load circuit which simulates a load to keep everything from short circuiting. From that load circuit it's going to send power to a signal modification circuit. That signal modification circuit takes this power source and converts it down to usually about 5 volts of DC power. That 5 volts of DC power now passes through an optical isolation circuit. Well, this isolation circuit isolates power from the power side right here from the power from the utility side. It isolates the power from the input side from the CPU. So the CPU power is a cleaner power. It's filtered, it goes through a power supply. If both of these powers connect directly, it's going to fry the CPU. The CPU just cannot handle the dirty power. So now, as long as there's no current flow, this optical isolation circuit does not turn on. Well, optical isolation has an infrared light emitting diode that shines its light on an infrared phototransistor. So when that light turns on, it tells the CPU that terminal is turned on. Well, that CPU turns on the LED that's going to be on the front of the PLC. And once that LED turns on, that LED symbolizes that this input has been closed. So now, we close the input. You now have a current flow through the circuit. That current flow turns on the isolation circuit. The LED on the front of the card turns on. Well, this LED is pretty much definitive. If this LED is on, this input is closed. If this LED is off, this input is open. The only way to turn this LED on is to energize an input. That's the only method to turn that LED on, is energize the inputs. Now, simple operation, how that works. Well, we close the input and now we got current circulation through the terminal points. That current passes right through the load circuit, which simulates a load. It's a small resistor. Passes through another circuit, usually a bridge rectifier, that actually converts the AC power to DC power. And from there it goes back to the power source. Once that power is converted to a 5 volt DC, that power flows through the optical isolation. It energizes the optical isolation, sends a light signal to the other side of the isolation circuit. That turns on the circuit, telling the CPU that terminal is turned on. Well, it's not a complex operation. It looks complex, but it's actually not as complicated as it looks. Now, the outputs are very similar in how the outputs work. One side of the power source is connected to the common terminal of the outputs. The other side of the power source is the return. Well, this power source right there, this type of card, could be virtually any voltage. It could be 120 volts, it could be 24 volts, 240 volts. It could be AC, it could be DC. At this point, it really doesn't matter because they're all going to work the same way. Now, we have the output connected to any one of the screw terminals, any one of those screw terminals. Now, as long as that screw terminal right there is de-energized, this LED over here on the side is going to be off. But this circuit works backwards internally from the input circuit. It works a little bit backwards. Right here we have the load connected to the power source and the screw terminals. The load, instead of connecting to a signal modification circuit, connects to a switching circuit. It again has the same optical isolation circuit and again has an LED on the front of the card. Well, this one works a little bit backwards. If the CPU determines that that output should turn on, it's going to apply 5 volts through this circuit. So it's going to turn on the LED and energize the isolation circuit. The isolation circuit right here is going to turn on, sending power through that circuit, closing the relay, energizing the relay coil. It turns on the transistor, it turns on the triac. Once this switching circuit turns on, whatever this power source is going to circulate, turning on the loads. Every PLC is going to operate in the same manner, no matter who made it. It's the same type of circuitry on both the inputs and the outputs. So now this LED turns on, this LED is controlled by the CPU. If this LED turns on, this load should be on. Problem is, this LED can be on and this load could be off. Well, this load could be burned out. I could have a bad connection. I could have some kind of problem with the rewiring at any point. I could even have a problem with the power supply. This indicator light on the output cards is suggestive. This output light indicator says this load should be on. It doesn't mean that it is. In many cases, this load is on, right there, light's on, and we're wondering why it's not working, so you got to go take a walk to verify that circuit's getting power. So there's a difference in inputs and outputs in the lights and what the lights mean. So right there, that 5 volts comes from the CPU. It energizes the LED on the front of the board, passes on and energizes the optical isolation circuit. The isolation circuit now turns on the switching circuit. The switching circuit now passes the current through the load circuit. The only way this light comes on is by the CPU, and this indicator light says this load should be on. If that load is not on, we can have a problem somewhere. Now, testing the inputs and outputs, again, does not have to be that difficult in how to test these. Now, one lead of the input right there is connected to the common power source. The other side of the power source is connected to the cards. As long as this input is open, there is no current flow through this portion of the circuit. Okay, this indicator light would be de-energized or off. If I take a measurement between these 2 points, I'm really not going to get anything on the meters because there's no flow of current. But now, once the indicator light turns on, well, if this indicator light is on and this load is open, I get a voltage here. Problem here is with this voltage, this light on and this load open, it shouldn't be that way. That light should turn on only when this load is closed. So if this indicator light is on and I get a voltage on that terminal with this load open, this input open, we got something miswired. This terminal's getting power from somewhere. You got current flow coming from somewhere. Now, right here when this circuit is closed, the input is closed, the indicator light should be on. If I get 0 volts on that terminal strip with that indicator light on, right here, that would indicate a defective card. Something is shorted out internally inside of the card itself. Now, almost all indicators we're taking measurements on the terminals for both inputs and outputs. So it's kind of easy to identify and diagnose. Well, for this indicator light to turn on the front of the card, front of the PLC, this input has to be closed. So if this light is on and this input is open, something internally in the card has failed. And that's rare to happen, but it does. Now, normally I'm taking a measurement across the circuit. I should get 0 volts on the outputs. Now we're going into output terminals. Well, outputs, all the outputs connected to the terminals, power source connects to the terminals. We're measuring from common to the terminal. Well, between this common terminal and any one of these screw terminals, this is going to be the switching circuit. This could be a relay, it could be a transistor, it could be a triac. It could be any one of these. But measuring from common to this terminal, I should get 0 volts on the meter every single time. The block diagram shows the same diagram, but now the diagram works backwards. It's the CPU that provides 5 volts through the circuit. That 5 volts will turn on the LED on the front of the cards. It energizes the optical isolation circuit. As soon as the optical isolation circuit energizes, it activates the relay contact, transistor, or triac. Once the switching circuit activates, it takes whatever power source this is and allows power to circulate through that source. This power source could be anything, 24 volts, 48, 120, 240, 277. It could be virtually anything, AC or DC. And yet, the circuits over here are going to be about 5 volts. So they are isolated from each other. Now, taking a measurement, if I measure from common to the screw terminal, I should get the voltage of the circuit, 24 volts. The indicator light should be on. So if this indicator light is on, I should get a voltage at that terminal. If that indicator light is on and I do not get a voltage at that terminal, that's a problem. Now, a lot of times the indicator light's on and the terminal reads 0 volts. Well, because that 0 volts and that indicator light on, this would be a burned out point. The electronics on that terminal has failed. Now, there's also a lot of times right there, you take a measurement, you get the light on, you get 24 volts at the terminal, and the load is de-energized. So I take a measurement across the load, from the common to the load. And again, I get 0 volts. Well, if I get 24 volts at this point and 0 volts at this point, that's a connection problem. We're miswired, we broke a wire fell off, something came loose, we got a connection problem between this point. On an electrical drawing, it'll only show you one wire. So there's 2 points. If there's any place that the wires connect on the drawings, it'll show you a connection point. Now, here we measure again. We get 24 volts at the terminal, we get 24 volts at the light. The light right there, the load is de-energized, and now we get 24 volts on a neutral. Well, wait a minute. A neutral wire is connected to earth. That neutral wire should always read 0 volts. So if I get 24 volts to the neutral, or to the return, that tells me this wire is interrupted at some point. Again, miswired. Again, a wire came loose, a wire fell off. Okay, but we have an open circuit at that point. An open circuit. There's all kinds of load devices out there. Now, any kind of time we're testing load devices, guys, we need to have the power off. We need to have the power off. Now, I can take the load device out of the circuit completely, or I'm going to lift only one of the two wires. If I try to measure the load device with both wires attached, there are other devices in the circuit with a resistance. And you are going to measure parallel resistances. So by lifting one of the wires, we isolate that one component. So I measure across the motor starter coil, a relay coil, could be a light bulb, could be virtually any kind of load device. When I measure straight across, I should get a resistance. That resistance might be as small as 3 ohms, and it might be as large as 1500 ohms. The point is, I'm getting a reading. Okay, I'm getting a reading. If you're not sure that reading is correct, then you take the meter, the same meter, and measure across another resistance of the same make, model, and voltage. It will not be the same. Very rarely will it be the same. But if I measured 70 ohms on one coil and I measure another one, that reading could be anywhere from about 60 to 80 ohms. Very rarely will they be the same, but they're going to be in the same ballpark of numbers, very close to each other. If I measure one coil 70 ohms and I measure another one of the same make, model, manufacturer, and voltage, and it reads 450 ohms, that would be a problem. That would be a shorted coil. Now, if you ever see a coil that's shorted out, go buy lottery tickets. This is your lucky day. You got a better chance of getting hit by lightning, a better chance right there of winning a super lottery than you do seeing a coil that's shorted out. So that's very rare for that to happen. Now, if I measure across that load device and I see OL on my ohm meter, that would tell me that coil wire is burned out. Completely burned out. So we'll replace the coil. But now make sure we replace that load device with the same voltage rating. The same ratings. What I have here is the Direct Logix PLC, and I'm going to turn on a couple of loads. Right here. And we can see that right here the Y, Y0, Y1, Y2, these are the output circuits. Those are the output circuits. Y0, 1, 2, and 3 are outputs. Now we got the Y3 on. Now they're off. 1, 2, 3. Now, right here on this Direct Logix, we're going to measure the terminals. I have several terminals on, several terminals are not on. So now the lights right here, Y0, Y1, 2, and 3 are on. Now they're off. Y0 is on, Y1's on, Y2's on. Taking a measurement on these terminals, I'm going to measure right here from the positive wire going in to the terminal itself. We measure terminal 0. I got my 25 volts, 24 volts. I measure terminal 1. I have the 24 volts. Measure terminal 2, 24 volts. I measure terminal 3, and I do not have 24 volts. I have an induction voltage. Very low induction. Yet I push that button again, and there that terminal comes on. So I can take measurements right here at the terminals. If I get a measurement, a voltage measurement at those terminals, well, the CPU and the cards and the terminals are good. If this light is on and I do not get a measurement on those terminals, then we have a problem with the terminal itself. So it's kind of easy to troubleshoot as long as we understand exactly what we're doing. Voltage and current, wattage as the last. If we change the ratings, we change the characteristics of the control circuit. You change the characteristics of control circuit, other devices are going to burn out. We measure a solenoid. A solenoid is the same thing as a relay coil. It's a large coil of wire. The only difference is that solenoid right there will control a process that is other than electrical. It controls a different process. So it has a different symbol. You measure across the solenoid again, pull it out of the circuit or unland one wire, and you will get a higher reading because you're going to have a little bit more wire in there. Solenoids might range from about, let's say, 3 ohms to about 1500 ohms. The higher the resistance rating is going to be a voltage. The higher the voltage. The higher voltages have higher resistances. So the point is, I'm getting a reading. Now, if I take a measurement across the solenoid and it reads OL, that solenoid's burned out. It's kind of simple right there. It's burned out. So we can measure output devices very easily. Now keep in mind, we can measure any output device in the same methods. It's just a matter of being able to either remove the device from the circuit or unland one of the wires so we don't get parallel resistance. We can test all kinds of inputs, push buttons, selector switches. Virtually any kind of a switch can be tested in this manner. We have the meter on ohms. We have a normally closed button right here, and I measure across the terminals. It reads OL was 00 or a very low resistance. That button's good. I activate the button. Oops. Jump through a few slides. I activate the button, and what I get is OL on the meter. So now the meter reads OL. So I can test these anyway. I could have a normally open push button that reads OL. Once I push it, it reads 00. Selector switch. Normally closed, 00, normally open OL. And no matter what I do, going back and forth with any kind of button, control device like this, it's going to read the same thing and test the same way, right across the terminals. And again, if you're going to do this, unland one wire so you don't read parallel resistance. Contacts are going to be everywhere. These could be on relays, they could be on limit switches, they could be virtually on any kind of mechanical device. Here we have contacts, any type of mechanical device. Normally open contacts, when they're measured across the contact, will read OL. Once you activate manually the contact, and many of these you can, you will read 00 or a very low readings. Normally closed contacts will read 00 across the contact. And if I manually operate the contact, it's going to read OL. And these contacts could be on anything from relays to limit switches to you name it. There's not a whole lot of control devices out there, but they all test the same exact way. So no matter what we do here, it's not going to be some kind of rocket science to actually make this kind of test.